So in the beginning of the talk, I showed what code for a proof assistant looked like. I showed a theorem, which was a very simple theorem, said that 0 was the right identity for addition. So for all n plus 0 equals 0. And I said, well, why is this hard to prove at all? The reason being that plus was user implemented. It's user written code. It's not built in. And it was structurally recursive in its first argument, which meant that the expression n plus 0 could not be simplified without knowing more about n. So certainly in the context of for all n, you couldn't simplify n plus 0. So I showed the proof in Coq that this was done, and the proof uses induction on n. And then there are the two cases when n equals 0 and when n is the successor of n prime. And in the successor case, you have to show that successor of n plus 0 equals 0, knowing that n plus 0 equals 0. And in the proof, there are a couple of lines that say simplify and then do a rewriting, a substitution. And then I revealed that what looks like a proof in Coq is actually a proof script that creates a proof object. The proof object is, when we look at it, a function in a functional programming language. And the type of that function is what we were trying to prove. So a proof of a theorem turns out to be a value which has a type. And so proofs are values or programs, and propositions or logical statements are types. And it's this correspondence that we use in order to create the proof assistant Proust, which is simultaneously checking types of a simple programming language and having students write proofs by programming and checking their proofs by doing type check. That's the beginning of the talk.
Thank you.
Implication gives us a successor of quantity n plus 0 equals n. And if we do a rewrite of n plus 0 by n, which we have in the inductive hypothesis, then reflexivity finishes things off. I could live code this, and you could see Coq giving you all this information that I was saying. This is what we know at this point. This is what we know at this point. And it all looks very nice, but this is not the proof. This is, in fact, a proof script that is instructing Coq to create the proof. There is a proof object that it creates. And normally that's hidden from you. You don't need to know about it. But you can look at it. So if we ask Coq to show us the proof object, it looks something like this. And this looks kind of strange. If we stare at it enough, we can see, well, plus right ID, which is the name of our theorem, is some sort of function consuming a natural number and doing something. And down here is the type of that function. And the type of this function written in a functional programming language that uses dependent types is the statement we were trying to prove. So this is an example of what's called the Curry-Howard correspondence, which says that a logical proposition can be viewed as a type in a particular type system. And a proof of a proposition can be viewed as a value that has that type. And a value that has a type is sometimes just a simple value, but often it's something like a function or a program. In other words, propositions are types and proofs are programs. And this is the idea that underlies a proof assistant like Coq. Now this is not quite enough to understand, but it's a start. So I knew this going in, but I wanted to know more. I wanted to know what was happening when I typed all those commands into Coq. What was it doing underneath? So in order to demystify, I had to write was essentially a type checker, because checking a proof is type checking if proofs are programs. It's a type checker for dependent types, so I had to understand how to do But I did that, and that was a lot of fun. It's always fun to write little bits of software that you can tinker with and actually do something. And then, as I was doing that, I realized that I had maybe solved one problem. I understood more about what proof assistants were doing. But this could be a solution to another problem I was thinking about, which is, how do we teach logic in the core of a computer science undergraduate program? Now, just about every computer science program on the planet has some sort of discrete math course. And it's usually a grab bag of logic and combinatorics and some probability and maybe some program verification, all done in one semester very quickly and very shallowly. At Waterloo, we're fortunate. Computer science is within a faculty of mathematics, so our students take real math courses from real math professors, and we don't have to teach such a course. But we do have a course called Logic and Computation, where we try to connect the ideas of logic to computation itself. And that course is not as successful as it could be. And those of you who were undergraduates in our program, I know some of you were, will probably know that I'm exaggerating on the modest side. That course is loathed and feared by students. It's horrible most of the time. Occasionally it's done well, but most of the time it's not. What's the problem? Logic is a perfectly nice subject. What's wrong? Well, for one thing, there are a lot of things we can teach. You can teach a course that's very highly mathematical, which is just focusing on propositional logic, predicate logic, soundness, completeness, models, etc. You can teach a course that's very applied, focusing more on, let's say, program verification. You can teach a more engineering style course. There are lots of extra topics you can throw in if you're interested in something like resolution or SAT solvers. It's easy to spend a lot of time on these things. So the content is inconsistent from offering to offering. People do their own thing. And students find working within formal systems very confining. They're used to writing mathematical proofs where they can wave their hands a little bit. They can say things like, the other cases are similar, or without loss of generality. Can't do that in a formal system. You have to write everything down. It's kind of boring to write everything down. It's kind of tedious. And it turns out that in many cases, it's a lot of work to prove even simple things. And so students say, this is not relevant to my experience. It doesn't connect to everything else I'm doing, which is trying to write a lot of software really quickly and get something working. And to be honest, that's what a lot of employers want. They want software quickly. So they say, well, this proving stuff, sure, it certifies software, you can prove things about it, but it's impractical. We will never prove anything on the job. So why are you making us do it here? And all of these are legitimate points. Now, I can argue back about whether school should be preparing you exactly for your first job or even your first co-op term, or whether we should be doing more useless things for long-term gain. But these are points that can't dismiss. So, can the Curry-Howard correspondence help in the study of logic? This was my question. And I said that the students don't like formal systems, and this is by and large true, but there is one formal system that they have thoroughly bought into that they enjoy, and that is a programming language. They like programming. They have accepted the fact that a programming language has a particular syntax, and if you don't use it properly, your code won't be accepted. They have accepted the fact that if you make a type error, then the compiler has a right to reject your program and not even run it. All these things are perfectly fine. So maybe they don't want to write proofs, but they want to write programs. Maybe they don't want to debug proofs that aren't correct, but they're willing to debug code that isn't correct. So this is my idea. Develop Proust as a type checker as I'd written it, but also as a proof assistant. So students can write proofs that look like code, and then that code is checked by Proust, doing type checking and proof checking at the same time, because they're the same thing. The students will actually see the code of Proust, because there's not much of it, as I said, and they will themselves implement parts of the system. They'll write code themselves. And then they can use that code to prove things. So what would be normally a pencil and paper assignment in a logic course becomes a programming assignment. So I'm going to describe the system to you and show you some pieces of it. We'll start out with propositional logic. And in fact, we'll start out very simply with just implication. If A, then B. A implies B. This is normally written with an arrow for implication. So T implies W. And I'm going way back to an interpretation of the logical connectives. That's work of Brouwer, Heiting, and Kolmogorov from the 1920s. And said succinctly, it says a proof of T implies W is a construction transforming a proof of T into a proof of W. How do we prove an implication? If T, then W. Well, you assume T, and then you use that assumption to prove W. When you do that, you don't have a proof of W, really. You have something which has, at certain points, uses the assumption that T holds. But if someone gave you a proof of T, you could take all those points where the assumption held and put that proof in at those points. And what you would get is a self-contained proof of W. That idea of taking a proof of T and putting it into something to create a proof of W is a function that takes a proof of T into a proof of W. And it's nice that function from T to W is written also with an arrow. It's a typographical coincidence, but we've just discovered there's something deeper there. So how do we represent proof terms? The traditional choice is what's called the simply typed lambda calculus, which looks like this. So this is a function from T to W. Lambda means we're setting up a function. It doesn't have a name, but it has a parameter called x of type T, so x colon T, and then a dot to separate it from a body expression B, which could be a complicated expression that uses x, and is supposed to produce something of type W. Now, this type annotation is something that we're used to from programming languages. But as it turns out, when we try to do this for logic, the annotations get really large, and I wanted to try to spare students that. So instead, I take out the type annotation and just say lambda x dot b, which means that some sort of type inference has to happen. Now, the type inference that we're doing here is very simple type inference, not anything close to what languages like Haskell or OCaml or Scala do. It's extremely simple-minded. And what happens is we have, our software has, or our rules have sort of two mutually recursive modes. In one mode, we're trying to check, we're given a type and we're trying to check whether a term has that type. But as part of doing that, sometimes we have to infer additional information. So there's type inference where we're just given the term and we have to figure out a type that works. And what we do in a lecture is create what I call what's traditionally called a bi-directional type system. One direction being inference, one direction being checking. And if you write down the rules carefully enough, the algorithm is entirely syntax driven. Just by looking at the term, you can figure out which rule applies, which means the software doesn't have to be smart. It just has to do what the rules say. I'm not going to show you the rules because I'd have to describe the notation. In a talk this length, I just can't do it very easily. But the rules are fairly simple, and they represent the kinds of logical inference steps that when you're reasoning about something, you do all the time. We're just formalizing them. The rules are, in fact, the rules of natural deduction, which is due to Gerhard Gentzen around 1935. For each logical connective, like and or not implies, there are one or more introduction rules and one or more elimination rules. An elimination rule is how to use something created by the logical connective. So for implication, we've seen that an implication, in order to create an implication, you create a function, a lambda. And in order to eliminate an implication, how do we use an implication? How do we use A implies B? Well, if we know A as well, then we can conclude B. That's the classical logic rule called modus ponens. If we know A and A implies B, we get B. That's function application. If we have a function, A to B, and an object of type A, and we apply the function, we get something of type B. So implication elimination is just function application. So what we see is that the rules are creating things that we know about from code. In this case, building a function and applying that function. And this pattern continues. We're going to build a version of Proust that just handles implication, and then add the other logical connectives. And this is how I do it in the classroom. So here's a logical statement. A implies B implies B. And you can view that as a function type. A function that has a first argument A, second argument of function from A to B, and produces something of type B. And here's the lambda term which has this type. It has one argument x of type A, and then one argument y of type A arrow B, and then we take that function of type A arrow B and apply it to the thing of type A, and that gets us something of type B. So this is a proof term for this logical statement. Equivalently, this is a program that has this type. Now, it's a program. I keep saying it's a program, but we don't actually run these programs. We're not actually computing at this point. And it would be legitimate to say I've just discovered or I've just created a very concise notation for trees, and we know that programming languages, programs are just trees, right, with some grammar. And that is true so far, but as we continue, computation will come into it. Now, the implementation is written in a language called Racket, which is a scheme dialect that happens to be what we use in first year. So all of our students have seen it. And so they already know how to code in Racket, and it also happens to be what I prototype in if I want to quickly create something, and that's what I did when I wanted to understand dependent types. So the user writes their programs in a language which has enough parentheses so that parsing it becomes very simple. So we have lambda, we have function application, we have a way of annotating an expression with a type in case a little bit of help is needed, and then we have the use of a variable. And then a type, right now we just have arrow types and variables. And we parse that into an abstract syntax tree using records. Here they're called structures in Racket. And this is the parser, which basically does a pattern match for each of the possible ways of forming an expression, and just does the obvious recursive descent parsing. The nice thing about this is that this is the only parser I ever show the students. When we add more things to the language, the students extend the parser themselves. And there's a corresponding pretty printer which goes the other way from the abstract syntax tree to a textual representation, and they extend the pretty printer as well. Racket really facilitates this because otherwise we'd have to, use something like Bison and Lex to write a parser, and that's messy. The Proust code itself is a very straightforward implementation of the rules. I'm going to show you the code. I don't expect you to understand the code, but I want you to see that it's fairly short. So here's the code for type check. It's there's really only one there's really only one case in type checking, and that's we have to check a lambda because we can't infer the type of a lambda. So this is just checking the type of a lambda. Otherwise, we flip over into type inference mode. And type inference has more cases. We cannot infer the type of a lambda, but we can infer the type of an annotation, an application, or just the use of a symbol. That's the whole code for type checking and type inference. There are 5 or 6 rules, and each rule corresponds to one case in one of these match statements. And all we need to do is parse the expression and pass it to type inference. And here's an example of how a student would write a test. Check expect is a testing form in Racket, and we just check that this check proof, when given an annotated term, where this is the lambda x dot lambda y dot yx we saw, and this is the A implies B that we saw, with all the parentheses put in. This will say, yeah, the test passes. This is the correct proof term for this statement. So we don't have very much code, but we have a very rudimentary proof checker. But it's not a proof assistant yet because there's no interaction. Well, Racket, like many functional programming languages, has a read evaluate print loop. It's a window where you can type expressions in and have them evaluated. So we add to the term language question mark representing an incomplete part of the proof, which is a hole or a goal. And we keep some state variables representing the current partially built proof term or expression, a counter in order to uniquely number goals so that we can refer to different question marks and tell them apart, and a hash table that maps the goal number to the type expected if you want to fill in that hole. And then we can, for example, set the current expression to be an annotated expression where there's a hole for the proof term, but we've spelled out the entire thing we're proving. And then we can take any one of these numbered goals and refine it by putting in an expression that itself may have more holes in it. So I know that this has to be a lambda because it's an arrow type. So I refine hole 0 with a lambda. Lambda x, where the body is a hole. I don't know what the body is yet. And now x has got to have type A, and that's kept in a context. And the goal, this question mark, is goal 1. It's now this part. A implies B implies B. And we can keep doing this. We type in a refinement, and that fills in the proof term more and more until the proof term is complete. And because we've been type checking all along, we know that it type checks. I'll spare you the live coding, and this is what the interaction is like. We set the task, we refine the first hole, we refine the second hole, and eventually we get down to having constructed the complete proof term for what we're trying to solve. Now this is crude interaction, but it's genuinely helpful, especially when we throw in the other logical connectives. And at this point, we have something like 80 lines of code, 60 to 80 lines of code. In the same way, we start reasoning about what the proof term should be for the other logical connectives. And the students do the implementation. Because once we have the rules, the implementation is straightforward. And this means they're invested in the process. They have built the tool that they get to use. So what's a proof of an AND? Well, a proof of T and W is a proof of T and a proof of W. So AND introduction just is a way of pairing, taking two things and grouping them together into a pair. And elimination is deconstructing a pair, projection of the first component or the second component. So these are familiar programming things, and yet they are exactly what is needed in proof terms in order to handle the AND connective. What about OR? A proof of T or W is either a proof of T or a proof of W. So an OR introduction is an injection into a tagged union, or if you know Haskell, this is the either type class in Haskell. And OR elimination, well, you've got something that's a type T or a W. You're going to get either a T or a W, but you don't know which, so it's a case expression. So once again, this is a familiar programming object, and that's what is actually used in order to construct proofs involving OR. What about negation? Negation is kind of interesting. We introduce a logical constant called bottom, which is kind of like a magic wand. There is no proof of bottom. It does not exist. A proof of bottom does not exist. However, if you have a proof of bottom, you can prove anything. Like a magic wand. Once you get one, you can do anything with it. But you can't get one. And the negation of T is defined as syntactic sugar for T implies bottom. That is, what is proof what is a proof of not T? It's an argument that says if you can give me a T, I can do anything. Therefore, not T must hold. And the rules are pretty simple for that. And that's it. That's natural deduction for propositional logic. Now, it's intuitionistic, constructive propositional logic. It doesn't have proof by contradiction. And it doesn't have law of the excluded middle. It doesn't say for all, A or not A does not automatically hold. Because just because you can't find a proof of A doesn't mean you should be able to find a proof of not A. That's not constructive. So there's certain things that cannot be proved in this system. On the other hand, we could add the law of the excluded middle and it doesn't result in an inconsistent system. It's just that there's no computational proof term for it. You can create a proof term, but it wouldn't work with what follows, which is predicate logic, adding the quantifiers for all and there exist. Now, this is kind of the point at which a conventional course starts to fall off the rails. Because it's very difficult to give coherent semantics for it that doesn't seem circular. And we tend to focus on first order logic, which is just not expressive enough, which leads to large proofs and all that tedium and boredom. So while predicate logic is really useful, but it's the point at which students start to lose interest. So in the course that I'm currently teaching, the goal with Proust is to be able to say in proof for all natural numbers n plus 0 equals n, which is that little bit of cock that I showed you at the beginning. So in order to do this, we rewind to just implication, no holes, and we do a bad refactoring. We had a nice grammar that separated terms and types, and now we're going to mush them all together into a single grammar. The reason is that if you look at this, this is going to be a type, and 0 is a term, but it's going to show up in the type. Plus is user code, so it's a term, and it's going to show up in the type. You can't avoid this mingling, so we might as well do it while we still understand what we're doing. So the grammar is now all stuck together. No separate grammar for types. We have lambda, we have function application, we have annotation, we have a use of a variable, we have the arrow type, and we have a type variable. And now type infer has to check that a type is well formed. So a lambda x implies lambda x, that wouldn't be well formed. But a arrow b, that is well formed. So type infer will check that, and if the type checks out, it produces some representation that says, this is a type. Well, what do we need? We need quantifiers for all there exist. We need things like natural numbers and other constructs to quantify over lists and whatever data structures we want. And we need computation. We need the ability for users to write things so that we can talk about proving things about programs. Typically, we do first-order predicate logic, and that only gives us the quantifiers. It doesn't give us things to quantify over, because quantification in first-order logic is over an unspecified universe. Higher-order logic is a better choice. And this is a bit of academic heresy, because everyone teaches first-order logic. Because the meta-mathematics of first-order logic, model theory, is really neat. Completeness and compactness and things of that nature. But it's not what the pioneers in the field used. It wasn't really, first-order logic wasn't really a thing until the late 1920s, and it took hold in the 1930s. And it's just a more natural thing to use a higher order logic. And it's what the proof assistants such as Koch and Agda use, so we might as well talk about it. Here's the difference. In first order logic, we would just say for all x and not say what x is ranging over, and then some property W that's true of all x. What we do is we quantify over a domain. So x is in the domain T. And that's the only difference. So what is a proof of for all x, T, W follows? Well, it's a construction that allows us to transform a particular little x, which has type T, into a proof of, see, W is something that's talking about capital X, right? It's some property of capital X. So it's going to mention capital X's. And if we have a particular little x of type T, what we need to do is substitute for all the capital X's in W, the little x. So we have this substitution where little x is substituted for capital X everywhere in W. So think about the case where W doesn't actually mention capital X. Then this substitution has absolutely no effect. It doesn't do anything to W. And so that means that in that special case, the construction transforms a value of type T into a value of type W. In other words, it's the implication rule. So when X is not mentioned in W, we just have T implies W. That's a special case of this. But when X is mentioned in W, the result type depends on the value of capital X. That's a dependent type. And so the proof term is just a lambda, generalized to allow this dependency that the result type can depend on the value of the argument, which typically doesn't happen in a programming language. So implication is a special case of for all. And as before, lambda introduces for all, whereas it used to just introduce implication. And using a lambda, using a for all statement, how do you use a for all statement? You stick a value into the for all. Like for all natural numbers n, something is true. Well, you stick 3 in, and then you get that statement about 3. That's how you use a for all. And that's just function application again. So we're on familiar ground, even though we've introduced this quantifier. If we add type as a constant in the user language, we can then write polymorphic functions. And we can quantify over propositions. A proposition that's talking about natural numbers is just a function from nat to type. Because what are things of type? They're propositions. But if we add type to the user language, it has to have a type too. And we choose type has type, which is a terrible choice. It's absolutely the wrong thing to do. It results in logical inconsistency. It sounds like this is something like Russell's paradox, but it's not. It's actually very difficult to show this. And in the first versions of Martin-Löf type theory, which is dependent type theory, the first versions of using this to talk about logic actually made this choice. And then after a couple of years, someone proved in a very complicated way with a construction showing that this resulted in logical inconsistency. What you really have to do is have a hierarchy of universes. So type 0 is an element of type 1 is an element of type 2, and so forth. And you have to figure out what level you're at in this hierarchy. But for tutorial purposes, this is perfectly simple. I mean, students are not going to be able to construct inconsistency and therefore prove anything. That would take way too much work.
That sounds like a challenge.
Yeah,
How
so
motivated are your students?
At least a couple of them said, if I can do this, do I get the marks? And I said, absolutely. You'll probably get more than that. You'll probably get into grad school or something like that. Well, we need more things. I talked about substitution. We actually have to implement it now. And if I say for all natural numbers n, something is true, and then I change all my n's to m's, those are exactly the same statement. The name of a variable doesn't matter as long as you use it consistently. That's true for functions too. The name of a variable in a lambda shouldn't matter as long as I consistently rename. So we need to be able to do that in order to talk about two types being equal. So we need a notion of what's called alpha equivalence. We've lost holes, and that has to stay away because it turns out that there are dependencies between holes, and it just gets too complicated to cover in a second-year undergraduate course. But instead, we can add a very simple definition mechanism, so we can have global definitions, giving names to subterms, which we can then use to shorten proofs. We also need some reduction to what's known as weak head normal form. If you don't know what that is, don't worry about it. But we need this idea that if you have a lambda applied to a value, then you should actually do the application. And this is the computation we're talking about. This is necessary in order to make two different types equal if they can be reduced to the same thing. And there are two advantages of this. First of all, we get computation, because this idea of applying a lambda when you know the value you're applying it to is exactly computation in the lambda calculus. And because there's some computation taking place, it doesn't have to be specified in the proof term, so proofs become more compact. So here's the complete grammar for our little language. We've added for all. We still have implication, but it's just desugared in the parser to an instance of for all where I make up a new variable. And we've added type. Tiny language, and yet this is a very expressive language. It turns out that it's possible to encode just about everything we want in a programming language. Booleans, pairs, natural numbers, and all the logical connectors. We don't actually need to, we could simulate them. Or, easier than doing elaborate simulations, we just add syntax for these things and reason about the rules. And this is what I do in the course because it's easier, it's more efficient, and the students can do the work once we agree on the syntax and the rules. So, what do we need in order to finish things off? We need equality. We need to introduce types of the form T equals W, because that transforms types into things that have true or false, a notion of or being provable or not provable. So equality is going to be witnessed by reflexivity when T and W are definitionally equivalent, which means we can reduce each of them down to two things which are syntactically identical. That's how we introduce an equality. How do we use or eliminate an equality? Well, that's substitution of equals for equals. And so what that says is if I have a proposition P and it's true of X, then for all Y such that I can prove X equals Y, the proposition is true for Y. that is taking an x in some statement, and because x equals y, replacing it with y. That's all this is saying. And this turns out to be exactly what you need in order to write the case in type infer, to infer whether a particular use of equality elimination is done properly, it type checks properly. And this is the code, which is a direct implementation of what we saw before. For natural numbers, we introduced 0 and successor, like we saw earlier, nat as a type, and the induction principle as the eliminator in order to prove something about all natural numbers who use induction. The induction principle says, well, if you want to prove that a proposition is true of all natural numbers, prove it for 0, show that the property is preserved by successor, that is, for any k, if p holds, then p of the successor of k also holds. And you can conclude that it's true for all natural numbers. That's mathematical induction that you're familiar with from your math classes. What is cool, though, is if p simply ignores its argument, that is, it's a constant function, what we get out of this is recursion, structural recursion on the natural numbers. So I can define a recursor using the induction principle once I implement the induction principle. I can use the recursor to implement addition. This is user code for plus. I can prove that 0 is the left identity of plus, and the proof term is simply reflexivity because this reduces, plus Zn reduces to n under the kind of reduction that we implement in order to do definitional equality of types. And finally, proving what we wanted, here's the proof that 0 is the right identity of plus, where we've implemented plus ourselves. And okay, it's a little complicated, but it's not too bad. It's certainly a lot smaller than the proof would be in first order predicate logic in a conventional course. Well, we could keep going. We could put the logical operations back. We can throw in lists. We can throw in your favorite data type. But at this point, the proof terms are starting to get a little awkward because working with these eliminators is not the most natural thing. It's kind of natural to come up with them, but to actually use them in a proof, it's awkward. So this is a good time to switch to a real proof assistant, such as Coq or Agda. Because we get holes and goals again, properly handled, which is complicated. There's a PhD thesis on the topic. Instead of working with these eliminators, they use dependent pattern matching, which is pattern matching where the result type can depend on what you're matching against. Instead of baking in natural numbers and Booleans, they provide a general way for users to define recursive or inductive data types, and then they automatically derive the corresponding pattern matching principle, which allows you to construct the recursor and the eliminator if you want, but you can also use the pattern matching directly in order to both do computation and construct propositions that can then be proved. And finally, instead of explicit proof terms, and we saw this with the Coq proof, the thing that looked like a proof that said induction, reflexivity, and so forth, was using tactics to construct the proof object under the surface. And both Coq and Agda do this. Coq much more than Agda. So, to summarize, Proust is a family of small racket programs ranging from 100 to 300 lines or so, depending on what level we're at, that act as rudimentary proof assistants. And they work to demystify larger proof assistants like Coq and Agda, and they can be used to teach logic as a required second-year undergraduate course to computer science students. So I'm in the process of doing this right now in my teaching. We have gotten through the entire Proust part of the course. I have just this week finished demonstrating, just today, finished demonstrating Agda, and on Thursday I start showing them Coq, and we have enough time left in the term that they can actually do some assignments in this proof assistant. And as I'm explaining what they're doing in Cook, I can harken back to what they did in Proust, and there's all these parallels, so they will understand what Cook is doing. It's not just this magic tool that does something that they don't quite understand. So that's my talk. It's a synthesis of interesting work by a lot of people, and there's a lot of really good tutorial material, expository papers, and videos and things of this nature out there, code repositories. So there's lots of stuff that I can point you at if you're interested in learning more. Thanks very much.
So did any of your students actually find the contradiction from the student type as type title?
No, it's really complicated to do.
It's surprising somehow. It's surprising that it's complicated to do. It feels, like you said, it looks like you should.
It looks like it should be easy, but it's not. So if you can write an infinite loop, you can get a contradiction. So what you have to do is you have to create a system where you can do general computation, or in some way create an infinite loop, and that's tricky without, you know. I can point you at the best explanation I know of. It's a book chapter. And it takes a bit of. There's no simple way to explain it. Yeah.
Could you talk a little more about applications?
So Coq is used a fair amount. It's got a lot of developments, a pretty big user community. It was built from the beginning with the idea that you would construct software in it, prove things about that software, and then extract the software to OCaml or Haskell, leaving behind the proof obligations so that there's no runtime penalty for it. And the OCaml compiler in particular is pretty effective. The biggest success of the Coq project has been the CompCert compiler. This is a certified C compiler. And what they have done is there's sort of three phases. There's the front end, which is the parsing. There's the middle end, which is the optimization. And that's where a lot of compiler bugs creep in optimizations, because it's easy to do an optimization that changes the semantics of the program. And then there's the code generation part. What they've done is they've completely certified the middle part of CompCert, and they're nibbling away at the front and back end. The back end requires some sort of model of like x86 or something like that, so it's gonna take a bit of work. There was a study a couple years ago by John Reguera and students at the University of Utah, and they used fuzz testing to create random C programs that they knew the semantics of. And then they would throw them at compilers. They threw them at GCC and Clang and CompCert and some others. The number of bugs they found in GCC was upward of 200, which is not surprising. The number of bugs in Clang was double digits, so 50, 60, that area. There were 7 bugs in CompCert, none of them in the middle section, all of them in the front or back end. So that's pretty impressive. Yeah, it's a C compiler that is certified. It actually does what it's supposed to, which is, and that's the goal. We're not quite there yet because there are a lot of things that are very hard to model, including a lot of things like interactions and networks and distributed stuff and dealing with memory and so forth. So it's work in progress. But the idea is a type system has always been there to have us to catch bugs early and to let us have more confidence in our software. If we make more sophisticated type systems, they can express properties of our programs, and that gives us greater confidence that our programs are actually doing what they're supposed to do. Yeah.
So I have a question. So usually when people use Coq, though, the standard library doesn't provide much functionalities, things like that. So for a mathematician to do his or her everyday work, there will be needed some more libraries, for example, algebraic geometry or anything. So are there actually people who create certain libraries for which one can just use the prompt? Because right now I have the feeling everybody who uses Coq just creates everything from scratch what is needed, and that is like a huge workload, right? So are there actually projects to just like, okay, everything that we know right now, to kind of formalize it into Coq? And
Yeah, there are projects doing
Okay.
that. Yeah, there are web pages that have collections of, the SS Reflect project, which is doing a lot of work in this area. I can point you at some web pages. I think there's probably, and of course there's the homotopy type theory stuff, which they're heavily using Coq for. So, yeah.
well, but that's a very natural application of it, right? So.
Yeah, but I think there are definitely these things happening. But again, it's not at the point where a lot of mathematicians can pick it up and use it as a natural tool. But we're getting there, I think. Work in progress. Yeah.
So, I know this is always hard to know, especially as the professor in a course, but do you have a feeling as to how successful this approach is being with the students with respect to the problems that this course has had historically that you talked about at the beginning?
So I am teaching it as an enriched section, which meant that I
cheating.
got, what?
So you're cheating.
Well, in a sense, I'm cheating. But I got to control who got into the course, basically. And there were a few students I said, you know, I can't guarantee that you'll understand this stuff. I would prefer that you take the regular section. But for most students, I let them in. So I think I have 50 students and I rejected 10 or 12 maybe at most. So they're good students for the most part. But I have asked to teach 2 regular sections next summer, and we'll see if they let me do that. If they do, I'll take some material out and stretch out, put more explanations, and be more careful about things. But I've been asking the students all along, sort of, you know, if you think this is reasonable and so forth. And the feedback I'm getting so far, you never get very much from students, but you know, I'll find out on the course evaluations. But the feedback I'm getting so far suggests that they're pretty happy they're taking it as opposed to a regular section, and that they think it has potential for actually working. Just the fact that I'm having them do programming in that course, and no one has ever asked anyone to do programming in that course, that goes a long way.
Well, this is your general habit, is to find courses named computer science and then some number and inject actual computer science into it.
Yeah, that is what I do. Yeah.
How this relates to, I was reading that in any cell phone, there is a part of firmware that has been proved to be correct.
In
any cell phone, yeah, for the SIM card software, yeah.
Oh, that's interesting. I hadn't heard that. So, I mean, people have been working on making models of various hardware components and trying to certify things about them as well. But I don't know to what extent Coq was involved in it. I should look into it. Okay, then, Stephen, I guess, where is he? He needs to talk next. Do we have a break, or?
Oh, yeah,
Yeah, yeah.
great.